All right, hi everyone. I got a question about the effect that adipose tissue thickness has on NIRS. So there's a series of papers out there that talk about this. It's important to know that when you use your NIRS device, that adipose tissue has an effect on your device. And one thing you need to know about your NIRS device is where's the penetration depth. So how far is the interop to the detector receiver spacing? Because half of this spacing is basically an estimation of your penetration depth of your NIRS device. That you're going to try to, how deep into tissue you can get a reading from. This is important to know because if your adipose tissue thickness, so your fat layer is thicker than your actual penetration depth of your device, you're not going to be ever measuring in muscle. If the goal is to measure in your muscle, you're just going to be measuring the fat layer and the skin layers. And generally, this isn't an all or nothing thing. So there's a certain relationship. So generally, the further the higher the fat layer in comparison to your penetration depth, the less sensitive your NIRS device gets to your actual muscle oxygenation. Again, if that's the goal that you want to measure. And I have some measurements I'm going to show you guys. And one of the things that I want to look at is I want to compare, so the Moxy, and I'm going to compare the Portamon. Those are the two devices that I use more often. And important here is, again, differentiating between a muscle oxygenation measurement where we're trying to say we're measuring muscle oxygenation. So we have to get into that muscle layer, and a tissue saturation where you're just measuring the tissue, which could include muscle or fat and so on. But you're modeling it potentially differently. So if you're measuring muscle oxygenation, you need to differentiate between, am I sensitive to the muscle layer, and where's the fat layer? I need to eliminate the fat layer and just see the muscle layer. Whereas tissue, if you're measuring tissue saturation, you could assume some kind of homogeneity. It's just you're measuring all throughout. So I'm going to put a series of graphs up, and these graphs, I've got these on this other screen here, so if I look over, please don't get irritated. So what these graphs show is they have adipose tissue thickness on the x-axis always, and on the y-axis the muscle oxygenation, or in the case of the Portamon, TSI. And we're looking at the minimal attainable values that you get after the arterial occlusion method or the physiological calibration. So after 5 to 6 minutes of an occlusion of tying your arm off, what is the minimal plateau that you reach? And this is a repeatable value that's pretty good to use. So you get to see, well, how does adipose tissue thickness affect the minimal value that I'm going to see? Okay. And what you can see is that as your adipose tissue thickness goes up, you actually have increasing minimal value. Okay, this is like, and this is from the Moxy here. So you become less and less sensitive to the muscle as you get more and more fat. And because the muscle is metabolically more active, even in included state, than fat or skin tissue, you get less signal from your muscle layer, you're going to have increased minimal values. I hope that's clear for everyone. But what's interesting is that you can now take this data and you can model these data points. Okay, so you can throw a linear model on it, which you have here, and there's a certain degree of linear model. But if we kind of look at these dots, you can kind of tell that it's not quite, it could be linear, but you do seem to have some kind of exponential increase once you get over once you get close to this adipose tissue threshold that I've marked on here. So the adipose tissue threshold that I've marked on here is 50 millimeters, which is kind of the recommended. Having 50 millimeters or lower is what the Moxy monitor says to have a good measurement for your muscle layer. So if you have 50 millimeters or less, once you go over that, you desensitize. So I can also model it exponentially. If I model it exponentially, you actually get a better model fit. And you can kind of see how once you kind of start hitting this threshold, you start really getting an increase in your min values, so a decrease in sensitivity. And the last way you can model it, which might make the most sense, is if I take a segmented regression. So if I say I'm going to do linear modeling, but I want to put one breakpoint into it, I get this result. And the breakpoint is essentially on this threshold marker. So it really shows that once you hit this threshold, you start losing sensitivity a lot more. And if you stay below it, you seem to get pretty good sensitivity to just muscle layer, which is what we want. And we can show this on a bunch of different muscles. So this was the vastus lateralis, but you essentially get the same results for the vastus medialis, for the gastroc, and for the rectus femoris, which is nice. What's also interesting is that this SVO2 threshold, which I put on. So the SVO2 threshold, just so that it's explained, SVO2 is mixed venous blood. So this is if you pull blood samples out of your veins, what is the oxygenation saturation there? What is the oxygen saturation in that pulled blood, in that blood draw? And this is from a study where after occlusions, they took blood draws and they looked at what is mixed venous blood saturation, and it was around plus minus 26%. So after 5-6 minutes of occlusion, you had an average mixed venous blood of 26%. Since mixed venous blood is a mixture of your fat layer, your skin layers, and your muscle layers that all come together, and your muscle is the metabolically most active part of that summation. If you have the summation equals 26%, you would assume that the muscle layer would have the lowest portion of that, whereas the other two parts would make up a larger portion of that, would make up a higher, maybe not more the total volume, but they would dilute the lower value into a higher one. And that's why you have this threshold marker. So the idea is that you should have lower values than this. Now, I don't know how much lower, there's no good measurements for that, but it should just be lower, which kind of creates this box where you have a box between your SVO2 threshold, so your mixed venous O2 threshold, and your adipose tissue threshold. And in that box, you should have that's kind of your legitimate measurement box. Let's call it, simply stated. So as long as you're underneath the adipose tissue threshold, your values for muscle oxygenation should be lower than your mixed venous blood values, and that seems to work pretty good over all the muscles. That's interesting. So this is somewhat goes towards validation, but it definitely helps us understand the effect of adipose tissue, and that you're going to get a good muscle oxygenation value if you stay under that 15 millimeter mark. If you go over, it's still usable, but the sensitivity goes down, and the value becomes less usable, and you start relying much more on trends. Okay, now quickly to finish this off, the same results, but this is just for the rectus femoris, but using another NIRS device to port them on, and let's see what we get. So you get these points on again. So generally we see much higher values. They're all over this mixed venous blood threshold. And it makes sense. Again, it's a tissue saturation index, right? It's taking all into account. This doesn't need to be sensitive maximally to the muscle necessarily for the definition of the parameter. And so it's very possible that all these are going to be higher values. Again, the method used is the same. And now if we model it linear, if you do a linear model, we have that here, but you can do the exponential model as well. And if you look at the exponential model, it looks almost like the linear model. It's actually a little bit, R squared is a little bit worse, but let's ignore that, it doesn't matter. But it's looking like the linear model. There's no clear difference here. So it's not like with the increasing adipose tissue, it's just a linear change to sensitivity. There's no, the relationship's linear. Unlike with the MOXIE, where you have a clearer exponential model with sensitivity change. And if you do the segmented regression, you actually kind of get an opposite. First of all, this is all underneath what Portamon says is the is the receiver detector spacing, which is 40 millimeters, so a little bit over 20 for this threshold, which is what we see here. This is all underneath their threshold of what they should be able to detect. But again, it's a tissue saturation and not a muscle oxygenation. So there's difference there. And you actually get this knot point made actually results in a flattening of your curve. So you get a much steeper increase at the beginning, and then it sort of flattens out, at least with this data set. But this knot point really has nothing to do with a threshold point, which is different from the MOXIe. I hope this helps differentiate TSI and SMO2, which I think is an important distinction, and helps you understand the relationship between your oxygenation value and adipose tissue, so you're aware of that. So because it's important when you're using the MOXIe. If you have any comments or questions about that, please ask me. I hope this was helpful. Bye-bye.